All right, so good afternoon, everybody. I wanted to let everyone know ahead of time, there is a small chance that class is going to be canceled next Tuesday. I think that's the 23rd. I plan to be here. Um, I, you know, I'm making every effort to come to class next Tuesday. But I have an appointment at 10:50 in South New Jersey, Edison, New Jersey, which is like about 45-minute drive from my house. Um, and so I'm actually very lucky. I'm actually got my vaccine appointment, so that's what that is. So I'm not blowing it off for just anything. So if it's at a mega site, yeah, I got very lucky. I just very lucky. Hopefully, like they open up to everybody like soon. But anyways, my wife and I have an appointment at the same time. We're very excited. So we're going to a mega site that's 45 minutes away. So if, I've heard things that like your appointment takes 20 minutes. I've heard things like your appointment takes 2 hours. So if it runs late, I won't be back in time. So I won't be able to contact anybody. Yes, Tuesday. Yep. So I won't be able to contact everybody because I'll be literally waiting in line. So I'll try. Yeah. So come to class. If I'm not here by 1:15 p.m., just consider class canceled. Okay. So that's on Tuesday. And I'll send an email reminder out about this on Tuesday. But does anybody have any questions about any of that? Okay. All right. So I'll shoot out a reminder Tuesday about that, but just come to class. Please wait 15 minutes. If I'm not back by 1:15, we'll just consider class canceled. All right. So if there's no questions, let's move on to our next topic. So the course is not our course is not cumulative, like in the sense that like you'll never be tested on, probability again, but like the topics still build off each other. So what we're going to move into today is what's called the uniform and normal probability distributions. Now, did everybody get a chance to look at the slides? I know I sent out an email about it. Were people able to download the slides a little bit before class? Okay, good. So you'll notice that a lot of the slides, unlike some of the previous weeks, like I'm just going to go real quick. You notice there's a lot of writing on here. So I'm just going to fill in the gaps in the slides as we go through them. Okay. So I like to say this about this section. I'm going to give a lot of definitions to start class, and for as long as I've been teaching this material, so I guess it's like 12 years now, it's always like, Matt, these definitions make no sense. What the heck are you talking about? And I know I've said this in this class. You ever feel like a lot of times I'll give a definition or I'll put something up there, and then after we do one or two examples, it's kind of like, oh yeah. That makes sense. Do you guys ever feel that way? Yeah. So it's going to be like that to the nth degree in this section here. Okay, so just let me get through the definitions, and then after we do one or two examples, it's going to click. Okay. All right. So what's the deal with this section? Okay. So last section, let me just put that up here. So last section, what we were talking about was discrete random variables. And what letter in mathematics did we generally let a variable be?
X.
Mm-hmm. All right, so it's going to be kind of the same thing here. So in this section, what we want to do is we want to talk about these things called probability distributions or probability distribution to continuous random variables. Okay. So have we heard the word continuous before in this class? It's been a while. What do you guys think? Okay, so discrete we've heard before, right? Discrete tends to be things like counts. Does anybody remember what continuous data or continuous variables were? Started with an M.
Like heights?
Yep. So measurements. Yep. Yep. Ken's got it in there. So these continuous random variables tend to be things like measurements. Okay. And exactly like height. Okay. Amount of rain that's going to fall today. Anybody, is it raining where everybody else is? It's pouring where I am today. So it's things like that. So yeah. So when we were doing continuous random for discrete random variables, okay, the probability distributions were shown as tables. Okay, so what we were doing was we were doing X, and then we were writing their corresponding probabilities, and that was the probability distribution for that random variable. Okay, and I think like we did on the exam, I think there was a life insurance question. You got to practice it on your homework. So we're going to kind of keep with this idea of a probability distribution, but here's the thing. For continuous random variables, it's like night and day, how we show their probability distributions. So instead of tables like this, okay, that we've been using, we're going to use curves. Okay. So we're going to be drawing a lot of curves going forward. And people in every semester, I hate to say this, but everybody gets sick of me saying the following thing. Okay, you're going to hear me say this a lot. What should we do first? Sketch the curve. Sketch the curve. Sketch the curve. And by like 2 weeks from now, you're going to be like, Matt, please stop. We know that we have to sketch the curve. Okay, so it's going to be using curves to show this probability distribution. Okay. And this is kind of like where we start even now, kind of like, oh man, what do you mean? What are you talking about? Curves to show a probability distribution? Like, you just got to let me get through the next couple definitions. And once we get to the first examples, I promise it always makes a lot more sense. Okay. Is everybody okay if I go to the next slide? Everybody good? Madam Melissa says she's good. Everybody else okay? Unless I hear something in the chat, I'll assume everyone's okay. Thanks, Taylor. Okay, so this is the first example we're going to work today. Okay, and I'm going to use this example to help us drive home the concepts. Okay, and it's a very, very simple example. Okay. All right, so here's the problem. Suppose the United Parcel Service, UPS, okay, is supposed to deliver a package to your front door, okay? And the arrival time, they say, look, your package is going to show up on your front door, and they're 100% sure about this, okay? They say, look, your package is going to show up on your front door sometime between 10 and 11 a.m., okay? So here's the thing. Do I know... let me ask this. How long is the window that they're saying my package will be? Like, how long of a wait time? What's the max wait time they're giving me here? Like 1 hour. Yep, I have a 1 hour window. But now here's the thing. When they say sometime between 10 and 11, okay, do I know exactly how long I'm going to have to wait for my package? So like, here's the thing. I could wait up to an hour, right? Like it shows up at 11, but could it show up at 10:30? Could it show up at 10:01? Yeah, it's like a range. So like there's this whole range of values in here. Sorry, hold on. I just got to close my email. There's this whole range of, oh, why did I just minimize it? I meant to close it. Jeez. There's this whole range of values. So I don't know how long I'm going to end up waiting. Okay. So I'm going to define this random variable. Okay. So I'm going to let the random variable X be equal to the time from 10 a.m. when the delivery is supposed to take place. So I'll change it up a little bit. I'm going to let the random variable X be the time spent waiting. Okay, in minutes. All right, from 10 a.m. Okay, like imagine it's like this super important package that you want to get. Okay, it's like your new PlayStation 5 or something. Okay. All right, so what is the least amount of time that you could spend waiting? 0 minutes, right? It shows up right at 10 a.m. You're like, sweet, I got my Xbox 5. Okay. All right, and what's the most amount of time you could spend waiting? Yeah. Okay. So the package could show up right at 10 a.m. You spend 0 minutes waiting, or the package shows up at 11 and you spent that whole 60 minutes staring out your window saying, where's my package? Okay. So we're going to expand on this a little bit. We're going to say is that all 1 minute intervals between X is equal 0 and X is equal 60 is likely. Okay. Is equally likely. So what that means is just like your package is equally likely to arrive between 10:15 and 10:16 as it is 10:41 or 10:40 and 10:41. Okay. Like it's just a unit. This will make more sense in a little bit, but it's a uniform wait time. Okay. No interval is more likely than the other. Okay. All right, this must be you must really want this Xbox to be waiting for it. Okay. All right, so first, just before I go on, X here, this is not a discrete random variable because it's time. It's a measurement of how long you spent waiting. So this is a continuous random variable. Okay. Continuous random variable. Everybody okay if I go to the next slide? Okay. So here's the question for today. All right. And please do not overthink this. Okay. So what is the probability the package arrives sometime between 10 a.m. and 10:30? Okay. So I'm asking you a probability question. Probability arrives between 10 a.m. and 10:30 a.m. Does anybody have a guess what the answer is? Melissa, why? That is the correct answer. Why is it 0.5?
Well, because it's the half of the 1 hour, which is the whole interval.
Yeah. So I'm just gonna rewrite this for you. Okay. If it shows up at 10 a.m., you waited 0 minutes. Okay. If it shows up at 10:30, you waited 30 minutes for this package to arrive. Okay. So I want to find basically this question is the same thing as the probability that time you spent waiting is somewhere between 0 and 30 minutes. Okay. And that totally makes sense. Look, the whole range is 60 minutes. I want to find you're going to wait the first half an hour. That's half the time. The answer should be 0.50. Okay, so what I want to do now is I want to make this problem super complicated, and everyone's like, "Oh, no, don't do that." I want to start giving all these definitions, and then I want to relate it back to this problem to show that all the definitions and all the weird stuff that I put up there, like, really works. Okay, that it's not all hogwash, and that everything works out the way it's supposed to. Okay. But before I go on, does this make sense to everybody? Why, if it shows up between 10 and 10:30, the probability has to be 1/2. Make sense? At least a little bit? I hope so.
Yeah, can you explain it again, please?
Sure. Okay, so X. Can we all agree that the most time you can spend waiting is up to 60 minutes. Okay, does that make sense?
Yes.
Okay, so think about a number line from 0 to 60. Okay, I want to find the probability that the time you spent waiting is between 10 a.m. and 10:30. Okay, well, so that's from 0 minutes spent waiting to 30. Do you notice how that's half of the number line here? So that's why the probability that you're somewhere between 0 and 30 is 1/2, because it's half the time. That's all. Does the number line help a little bit? Okay. So what I want to do now is I want to go and start with some definitions, and please listen to me on this. The definitions and everything is going to seem super weird at first and confusing, but after you see a bunch of examples today, again, it'll make sense. I promise you. Okay. So the first definition we have is something called a density curve. Okay. And a density curve is a curve that represents the distribution of a continuous random variable. Okay. So what a density curve does shows how some random variable like X is distributed. Okay. And there's going to be two common density curves that we talk about. The uniform density curve, which is going to be, and I'm just going to go back for a second. You can kind of see, when I say uniform wait time, I'm going to introduce something called the uniform density curve. And then we're going to spend a ton of time talking about the normal density curve. Okay. And what we're somehow going to do, going to relate a density curve to probability. Okay. So I'll come right back to this, but look, our question today is a probability question. So I'm going to use a density curve. I'm going to use a curve now to help us answer this probability question right here. Okay. Okay. So now the reason do you think every situation in the real world, just stop. Do you think every situation in the real world, it follows what they call a uniform wait time? Or is it like, do you think there's situations in the world where some time periods are more likely than other time periods? Yeah, totally. So, so we're going to need multiple density curves to answer problems. And we're just going to focus on two, but the two that we talk about in this class, just know that they're not exhaustive. Like there's a ton of other density curves if you continue your study in statistics. Okay, a little weird. Okay, totally weird. What the heck does this mean? I'll show you in a second. Is everybody okay if I go to the next slide? So next we have this thing called a probability distribution function, or it's also referred to as a probability density function. All right, a PDF, okay? I always call it a probability density function, but it's also sometimes referred to in certain textbooks as a distribution function, so I wanted to put it up there. And all this is some type of equation used to compute probabilities for continuous random variables. Okay. So look, going back, you can see, hopefully see where this is building. A probability for a continuous random variable right here. And now I'm going to get this equation, okay? And I'm going to use this equation to compute the probability of that. Okay, great. All right, we have this nice equation. So the thing is, this equation must satisfy the following two properties, okay? And these two properties are really important. The total area under the graph of the equation over all possible values of the random variable must be equal to 1. Okay, so if you think 1 in terms of probability, this is 100%. Okay, so the area under the curve, the area under the graph, okay, is 1. Okay, so it's equal to the entire probability across all possible values for the random variable. Okay, and the height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So what this means is our graph never crosses the x-axis. Okay, never goes negative. So the density curve that I defined on the previous slide, okay, is the graphical representation of this probability density function. Okay. All right, so just be honest. How many people are like, this makes no sense right now? Just let me know in the chat. Like, I don't know exactly what you're even talking about, Matt. And it's okay. It's like weird stuff, right? Okay. So at least one person is, yep. And what I want to say is, yep, please, thank you for being honest. Like, all of this stuff makes no sense until you see the first example. Okay. All right. Yep. I hear you. I promise. I always like to just, pad all this stuff as we go through it. Like, just keep this stuff in the back of your mind. Okay. So like, we have this density curve. And what this density curve does is it shows the distribution of a variable. Okay, that's a little weird. Not sure what that means yet. Now we have this thing called the probability density function, a PDF, and it's the equation of the curve. Okay, and we're going to use this equation to compute probabilities. All right, okay, a little weird. All right, so how are we going to use these density curves and these probability density functions? So the first thing that's going to happen is you're going to be given a probability density function. So remember, this is an equation. And then you're going to take that equation and you're going to sketch the density curve. Okay, so you're going to take the equation and then you're going to sketch the graph. Okay. So it's somewhat, not exactly akin to, like if I were to put up this equation, y is equal to mx plus b. Does anybody know what that's the equation for?
Line.
Yep. So this whole concept is like, look, I'm going to give you an equation, like an equation of a line. And then what you're going to do is you're going to take that equation and you're going to sketch the graph. Okay. That's kind of what's going on here. Okay. Second, what you're going to notice is that the area under the curve of the density function over an interval represents the probability of observing a value of the random variable in that interval. Okay. This is the most important concept of today's class. Okay, this right here. Like if you're going to remember one thing, I'm gonna kind of, you'll see below I have key concept in parentheses. Like I'm going to try to put it in layman's terms. Like if you're going to remember one thing from today's class, you got to remember this, okay? Because it's like the most important thing. The area under the curve between two values is literally equal to the probability the random variable x falls between those two values. Okay, so look, I want to find the probability x is between two values. Okay, do you see that? My random variable x is between 0 and 30. So what I'm going to do is I'm going to find the probability density function of this. I'm going to sketch the density curve. And then the area under the curve between 0 and 30 is going to be equal to this probability. Okay, that's what's going to happen. Okay, so just let me even make it a little bit more simple. Key concept. Area under the curve will be equal to probability. Okay, just like, you know, put this, like drill this into your mind so that you wake up in the middle of the night, like in a cold sweat, being like, area under the curve is a probability. Oh, I was having a nightmare from stats class. Like, that's how important it is. Okay. Actually, I hope class doesn't give you nightmares. That's not one. Yeah, that is an odd nightmare. Okay. But I've had odd nightmares too. So, you know. Okay. I hope that made somebody else laugh, though. All right. Everybody okay if I go to the next slide? All right, so we're going to go back, and now what I'm going to do is I'm going to introduce all these concepts of a density curve, probability density function, area under the curve being probability to our example. Okay. So we're going to go back to that random variable. Okay. So remember, the random variable x was equal to the amount of time in minutes spent waiting for package from 10 a.m. And here's what we said. We said, look, it's going to be some value between 0 and 60. Next, what I said was all two intervals of equal length, okay, between 0 and 60 are equally likely, okay? So this random variable x is said to follow what's called a uniform probability distribution, okay? And whenever you get a problem, like a homework problem, and I'll actually put up your homework right after class today, just so you can kind of get a head start on it, or take a look at it. It's going to say something like follows a uniform probability distribution. So you'll know to use this, what I have on the next slides here. Okay. All right. So x, this random variable x, you're going to see me use this notation. I'll explain in a second. This means follows or is approximately a uniform random variable. So everybody okay if I go to the next slide to give you the formal definitions now? Okay. So what is the probability density function, the PDF, for a uniform distribution? Okay, so remember what a PDF is. A PDF is an equation. And we denoted a P of X, so that tells me it's a probability. Yep, sorry. Of course. Okay, good. So this equation is what's called a piecewise defined function. So what that means is it just has multiple equations over different intervals. Okay, that seems a lot more complicated than it is. So a piecewise defined function gets set notation. in all a uniform distribution is equal to, it's very, very easy. It's equal to 1 divided by b minus a. And this is for x anywhere between a and b. And I'll explain all this. And it's just 0 otherwise. Okay. Think of a and b. Think of a as the starting value. And think of b as the ending value. So hopefully you can kind of see what a and b are from the previous example. Like, let me go back here. What is the starting value of x here? Right, my mouse is going. Yep. And what is the ending value of x here? Yep, that's it. Okay, so this equation, a and b, are just 0 and 60 from my example. That's it. That's all it is. Okay. So now the density curve, okay, for this uniform distribution, a density curve is the graph of the PDF. Okay, so if you were to sketch the graph of this equation, like what the heck would it look like? So it's actually super easy, okay? It's incredibly easy. So draw the first quadrant of the Cartesian plane. And along the horizontal axis, you get the values of x, the random variable. And along the vertical axis, you get probability, P of x. So look, anytime x is between a and b, so a could be any number here, b could be any number here, the function, the equation is equal to 1 divided by b minus a. So that'd be 1 divided by b minus a. So it would literally be a horizontal line for this whole thing. That's it. Totally, that's it. Just the graph is literally a horizontal line. And then it's 0 otherwise. So I'm going to put an open circle and 0, open circle and 0 all the way this way. So this graph, okay, literally just a horizontal line, okay? So how about I put some numbers to this now? So let's actually plug in for our example, okay? So let me know when everyone's ready for me to go to the next slide. All right, I got 2 readies. All right, so let's find the PDF for our random variable x and then sketch the density curve for x. Okay, and just remember, what is x? X is the time you spend waiting. Okay, x is the time you spend waiting. So the probability density function for x, it's 1 over. And now remember, x can go between 0 and 60. So 0 is my a, and 60 is my b, my ending and starting value. So it's 1 over 60 minus 0. Okay, this is for x between 0 and 60. And then what did I say it's equal to otherwise? Yep, 0 otherwise, everywhere else. So you can even clean this up. Like, what is 60 minus 0? Yeah. Okay. So now what I want to do is I want to take this equation and I just want to sketch it. And now I'm going to go back for one quick second. So all this graph is a horizontal line, okay? And it's a horizontal line over a and b, so over my starting and ending value. So you're going to put X and the probability of X. So X starts at 0. And what is its ending value again? Yep, just 60. And look, along the horizontal axis, you put 1 divided by B minus A. Well, that was 1 over 60. And then you're just going to draw a horizontal line. Boop, just like that. And then it's 0 everywhere else outside there. Okay, just a horizontal line above 0 and 60. Okay, so let me ask you this. Even though it might not fully like sink in, because this is just our first example, like, did the numbers actually just like not seem too bad to sketch this? And don't worry, we're gonna get to do another example too. Okay, so like, just try to like soak in as much as you can from this first example, and then the second we'll hit it home. Okay. Everybody ready for me to go on? All right, so watch this. This is going to be really cool. Okay. Does anybody remember what we said the answer was? The package comes between 10 a.m. and 10:30 a.m. What the answer was again? Okay, it's 1/2. All right. So watch how I'm going to do this. Okay. First thing I'm going to do is I'm going to write the probability statement. Okay, so this was the probability that X was between 0 and 30, literally. Okay. Next thing I'm going to do is I'm going to sketch the density curve. For X. So what I'm going to do is I'm just going to replicate this density curve. Yeah, it was. What did I just say? No, the answer is this 30 because I'm going to be waiting between 0 minutes and 30 minutes. The final answer is going to be 0.5. Yep. So here was 0, here was 60, here was 1 over 60. I'm literally just redrawing the graph. The third thing you're going to do after you do this is you're going to now, and I'm going to go back real quick. Don't worry, I'll come back. This is where the key concept comes in. Key concept. All right, the area under the graph of a density function, okay, over an interval represents the probability of observing a value of the random variable in that interval. Area under the curve is equal to probability. So what you're going to do next is you're going to shade in the area, shade area under curve over the values of interest. So look, I want to be between 0 and 30. So 30 is over here. So what I'm going to do is I'm going to shade the area under the curve literally between the values I'm interested in, between 0 and 30. And then the fourth thing is the area you shaded in is equal to the probability. Well, does anybody know what shape that red shaded thing is right here? It starts with an R and ends in rectangle. There you go. Yep. I just shaded in a rectangle there. Okay. So does anyone know what the area of a rectangle is? It's length times
Width times height.
Yep, length times width. Yeah, So length times width times height is the area of a. That's actually the volume of a cube. So the area of a rectangle is just length times width. Yep. So check this out. The length is this right here. Well, the length to go from 0 to 1 over 60 is 1 over 60. And can anybody tell me the width from 0 to 30? What is this width right here?
30.
Yep. So 1 over 60 times 30, you can write 30 as 30 over 1. So 1 times 30 is 30. 60 times 1 is 60. And look at this. 30 divided by 60 is 0.50. So I just took that problem that was really easy to begin with, that you would wait, the probability that the package would show up between 0 minutes and 30 minutes was 50%, and just made it much harder. Okay, so let me ask you this. Does it at least seem like how I used, or make sense a little bit, how the area under the curve ended up being the probability? Or does everyone see that it ended up being the same thing? Okay. All right. That's hard for me to see your faces, but when I was an undergrad and I got this, I was like, oh my God, that's so cool. I don't know if anybody else had that same reaction. It's probably why I went to graduate school for this stuff, but well, I hope it's not the coolest thing you've ever. I hope it is a cool thing. Okay. I mean, the coolest thing I ever saw was my wife coming down the aisle when we got married. Yeah, I actually cried like a baby, but we won't talk about that. Okay. It was awesome. Okay. Let me ask a follow-up to this, and then we'll take our break, and then we'll do another example to have this hit home. Okay. Everybody okay if I go to the next slide? Okay. All right. So same example here. Just a follow-up question here. So what's the probability the package arrives sometime between 10:30 and 10:45? Okay. All right. So if the package shows up at 10:30, how long did you spend waiting?
30 minutes,
Okay. And if the package shows up at 10:45, how long did you spend waiting?
45.
Yep. So look, first thing, write the probability statement. I want to find the probability that I spend waiting between 30 and 45 minutes. Okay. Step 2, you're going to sketch the density curve. So you could be anywhere between 0 and 60. 1 over 60. Horizontal line. 0 everywhere else. After you do that, shade area under curve over values of interest. So my values of interest are 30 and 45. So here's 30, here's 45. And then you're going to shade in that area. Well, check this out. So the probability is the length from 0 to 60. So length is 1 over 60. And what's my width here from 30 to 45?
15.
Yep. So this ends up just being 15 over 60, which is 1/4, or 0.25. And that's it.
Is there a way to do it on the calculator or no?
So unfortunately, not these problems. I know that's not something that's great to hear, but I will tell you this, and then we'll go on break. I got a private message. Why is 60 always included? Because you always put the starting value, which is 0, going back, in the ending value. You always have to put on the graph the starting and ending values, and then you put the other two values under the curve. So you got 15 again, because you have to find the width, right? So the width of this rectangle is the distance from 30 to 45. So is the 60 part of the formula, or we're using it because 60, we're using it because it's 60 minutes. Right? Yep, I got a bunch of questions shot to me. Okay. So the 0 and 60 come from, right? So the 0 is remember the 0 is how much time, or X is how much time we spend waiting. So if they show up right at 10 a.m., you spend 0 minutes waiting. If they show up at 11 a.m., you spend 60 minutes waiting. So the 0 and 60 are all dependent on the problem, the information that's given to you. So you'll see when we do the next example that you're going to have different values. You're not going to have 0 and 60. It's going to be just different numbers. Like, that's the hard part about this, perhaps, is like figuring out, what the values of A and B are to plug into your equation. Okay. And then there was a question about step 2, like, how did I get these numbers here? So the length of the rectangle is always this value here, whatever you have in your graph, in your equation. So this 1/60. And the width is always the distance between the two values here.
Oh no, Professor, I meant like step 2, like those when you drew the graph, then you at the bottom you made an arrow from 0 to the left, and then you made another arrow from 60 to the right.
Oh, so that's only because it's 0 otherwise.
Oh, that's why. Okay.
Yep.
All right. Thank you.
No problem. All right, let's take a 10-minute break. And then what I'm going to do is I'm going to come back. Where did the 30 and 45? So if they show up at 10:30, you waited 30 minutes. If they showed up at 10:45, you waited 45 minutes. Because remember, we're counting minutes from 10 a.m., like how long you spend waiting. They said they're going to be there at 10, anywhere between 10 and 11. So it's minutes you spend waiting for the person or the package. All right. And so look, I'm going to take a 10-minute break. And then what we'll do here is we'll come back and we'll do another example of this. And hopefully seeing a second example will help have this make sense, okay? All right, I'm going to step out for 10 minutes. All right, everybody. Everybody ready to finish up for the afternoon? Okay, so what I want to do during this second part of the class is I just want to do one more example of the uniform distribution. It's not the most used probability distribution for continuous random variables. So I just want to do one more example. All the examples for these problems are exactly the same. Just the only thing that changes is the numbers, and you'll see that in the next problem here. Okay. So here's the problem. Suppose that travel time from White Plains Transit Center to SUNY WCC on public transit. So this is bus route number 40. So whenever I take public transit to work, I always go on bus number 40. Has anyone ever ridden on bus number 40 before? I think bus numbers 40 and 41. Or is it 42? I don't remember. It can go to campus. So anyways, suppose the travel time from New York or from White Plains Transit Center to SUNY WCC on public transit, 40 and 41, thank you, follows a uniform distribution. Okay, so right there, this uniform distribution, okay, that tells me it's going to be exactly like the previous problem with the minimum time. So the minimum amount of time you can spend on the bus is 12 minutes and a maximum amount of time is 22 minutes. Okay. So let's let the random variable x represent the time from White Plains Transit Center to SUNY WCC on public transit. Okay. So watch how I define this. I'm going to let the random variable x be time spent on public transit. And what is the minimum amount of time it takes to get to campus? Like if everything goes perfectly, you hit all the lights, there's not that many people at stops, not a lot of stops are requested, okay? And what's the maximum amount of time? Yeah, look. And so look, going back to our previous problem, x was between 0 and 60. In this problem, it's just between 12 and 22. So you can think of this as my A, and this is my B, okay? And then once you got that figured out, do you kind of see like everything else is just going to be the same, just the numbers are going to slightly change ever so slightly, okay? Everybody okay if I go to the next slide? All right, so here's the problem. What is the probability density function for the random variable x? Okay, so that's this equation here. Okay, this is this piecewise defined function. Okay, so just going back, it's always 1 over b minus a. So for our problem here, it would be 1 divided by what minus what? Yep, b minus a. But what is my b and a? Yep, thank you. Yep, it'd be 22 minus 12. And this is always for x between 12 and 22. And it's just 0 otherwise. Okay. So look, you can even clean this up, right? What is 22 minus 12? I think it's 10, right? All right. So look, I've got my probability density function. Look, in the previous problem, it was just 1 over 60 between 0 and 60. Here, it's just 1 over 10 between 12 and 22. Like that's it. That's just the numbers change, and everything else is the same. So sketch the density curve. So you're going to have X and you're going to have the corresponding probabilities. So look, the values of interest or the values it can take on are 12 and 22. Okay, there's my A and B. I'm going to put 0 at the axis. And then it's 1 over B minus A, which is 1 over 10. And then it's just a horizontal line, literally from 12 to 22, where 1 over 10 is. And then once you get outside that, it's just 0. So it's just right at the axis here. That's it. All these problems are just a horizontal line. That's it. So the next question now is what is the probability the travel time is between 15 and 18 minutes? Well, watch. I'm going to go to 15 minutes. I'm going to go to 18 minutes, somewhere between there. And I'm just going to shade the area under the curve. So look, it's just length. What is the length? Yeah, the reason there's open circles, I got a private message about this. I don't know if you meant to send me private messages or not, but the reason it is because the open circles tell us to go like right up to 12, but not exactly 12. That's why there's closed circles up here. Yep. Okay, so the length here, it's 1 over 10. So notice in the previous problem, it's just 1 over 60. It's always whatever you have here on the vertical axis. And now what's the length or what's the width here between 15 and 18? Yep. So 1 times 3 gets me 3 over 10. This is just 0.30. Not too bad. Does it help a little? Better? I'm actually gonna add a slide in here and do just
The-
Yeah.
Just like, please.
Did you have a question?
Yes, please, I do.
Okay.
Yes, where you shared 15 and 18. Do we really have to do that for the third question, number C?
No, if you know it's just 3, you don't have to. No.
Okay, thank you.
Yeah, no. All right, I want to ask one more follow-up question to this, if I can just go to the next slide, if everyone's okay with that. Everybody good? Okay. And this is really interesting. The 1 over 10 comes from, it's just the difference between the max and the min time. It's the difference between A and B. So 20, the difference between 22 and 12 is 10. That's where the 10 comes from. And then it's always 1 over B minus A. Like that's where it comes from. So I just cleaned up the 22 minus 12 and wrote it as 10. Okay, good. So this is really important, this next part. For continuous random variables, you can only compute probabilities over an interval. Okay. Like, let me show you why. So imagine you take this bus and what's the probability your travel time is exactly 20 minutes. Okay, so you literally hop on the bus, the number 40 bus, and it takes you literally exactly 20 minutes from the time you step on the bus to the time you step off the bus, okay? So that would be the probability that X is exactly equal to 20 minutes, okay? So watch what happens when I sketch the density curve again. So we said the minimum time was 12. The maximum time was 22. 1/10 is here. So look, here's where 20 minutes is. Okay. So now if you were to use what I've been talking about in class here, okay, so the probability is equal to the length times the width. Well, the length is still 1/10. But what is the width of this line right here? Does it have a width?
0.
It's 0, yeah. So we can never, whenever we do these problems going forward, we will never ask a problem like, what is the probability that X is exactly some value? We will never do that. It's always going to be the probability between two numbers. Like it's always going to be that way. And which is why you'll notice sometimes, I'm just going to go back a slide. When I write things like, what is the probability the travel time is between 15 and 18? I can write it these two exact same ways and it's the same answer without the equal signs under the inequalities, because the probability that it's exactly 15 is 0 and the probability that it's exactly 18 is 0. So don't worry about like, if you see me stop writing the equal signs under everything, okay? And just write strictly less thans. All right, so I'm going to move on from the uniform distribution. You'll get a chance to practice this on your homework. I don't even think I ask a uniform problem on the next exam. Okay, you'll just get a chance to do it on your homework. The reason is, or I think I might ask one, but it's all these problems follow exactly the same way. The only thing that changes is the numbers. Okay, like the formulas are still the same. It's always 1/b minus a. And it's always a horizontal line as the graph. So what I want to do now is I want to introduce in the next half an hour of class that we have left or so, is I want to introduce the normal probability distribution. So is everybody okay if I go to the next slide? Everybody good? Good. One good. All right, so here's the deal. The uniform distribution is not often used in the real world. There's just not many things in the real world that have a uniform probability distribution. What's much more common, all right, and what we're going to literally spend, oh gosh, the next month, pretty much the next the next month of class talking about is this normal distribution. Okay, and you guys might have also heard this referred to as the bell curve. Okay, how many people have heard of the bell curve before? Maybe even seen it. Looks like this. Yeah, got a few. Okay, a few. Yep. Okay. There are a ton of statistical applications to the normal distribution, and It's just so important for advanced study in statistics. And we're going to talk about all the things that I've just talked about with the uniform distribution and related to this bell curve shape. Okay, so a continuous random variable X is normally distributed. Okay, so it follows the bell curve shape. If you look at the frequency histogram, and it's the shape of a normal curve, okay? So let me go to the next slide, and I'll show you what I mean by the histogram looks like a normal curve. Okay. So frequency histograms that are what we call symmetric, and what symmetric means is like if you were to cut it in half, the two sides on each side would be roughly the same, or actually symmetry means they would be exactly the same, but in this case, the histogram looks roughly the same. And they have this bell shape. So what that means is you can, if you superimpose on top of it, this bell curve shape, you can see that this histogram follows a normal distribution, okay? And that's all it's gonna take for in our course for something to be normally distributed. Oftentimes in the problem though, so often in our course, you'll be told that the random variable X is normally distributed. Like, did you notice in the last example we did of the uniform distribution, I said something like travel time follows a uniform distribution. Like when we work these problems going forward, the problem will say something like heights of adult males follow a normal distribution, or that they're normally distributed, okay? And then when you see that keyword, you'll know to use the methods that I'm going to talk about over the next couple weeks. Everybody okay if I go to the next slide? All right, so now here's the thing. What I want to do is I want to show you what the normal density curve is and what the equation is for the normal probability density function. Okay, so first off, in the previous example, when we were looking at the uniform distribution, its density curve was a horizontal line. Okay, when you have something that follows a normal distribution or is normally distributed, its density curve is no longer a horizontal line, but it's a bell curve. Okay. And the bell curve is centered at this value here. And that's the Greek letter mu. Does anybody remember what the Greek letter mu stands for in statistics? Anybody? Yep. Thank you, Jamie. Yep. And so what mu is going to be is it's going to be the mean of the random variable. I guess I actually even have it here. Okay. So this normal curve, this bell-shaped curve, actually has an equation that corresponds to it. Okay. And this is the equation for it. Okay. So if you were to take this equation and plug it into a graphing calculator or something, you would see this bell curve shape, but it's equal to this. It's 1 divided by the square root of 2 pi sigma squared, where sigma is the standard deviation. E, the number e, the exponential, raised to the negative x minus the mean squared divided by 2 sigma squared. Does that formula look crazy or ridiculous to work with? Yeah. It looks terrible, right? Yeah, like, if we go back just real quick, 1 over b minus a, that's pretty easy to work with. That's just a fraction, 1 over some number. But this crazy thing looks awful to work with, okay? So I have some good news for this, okay? We're going to do everything we had just talked about, drawing the curve, shading area under the curve, and finding probabilities for things that are normally distributed. But don't worry, okay? We're actually not going to use the equation, okay? Okay. I just wanted to put it up here real quick so that you know that there is a mathematical formula behind this equation, okay? Or behind this density curve that we're going to be sketching and drawing. And so we're going to compute probabilities, all right, using 3 ways, okay? The first way is going to be what I'm going to talk about in class today, and maybe with the time we have left, and then maybe one other example next class. And then I'm going to show you how to read statistical tables. Okay, so how to do problems by hand. It's also just useful to see a statistical table and learn how to read it. You never know if you're going to take another advanced statistics course in your academic career. And then I'm going to show you how to do this in your graphing calculator. Okay. And this way is the best and easiest way. Okay. But the thing is, the reason I show the graphing calculator last is, like, once you have a full understanding of how these problems are tackled, it then allows you to use the graphing calculator much more effectively and with a better understanding. Okay. So I'm going to burn through, how to do this by graphs and by hand. And then we'll only spend like half a lecture on the statistical tables. And then we're going to spend the rest of the time working with our graphing calculator. So next class, make sure you bring your graphing calculator or have it handy with you. Okay. All right. So what I want to do now is I want to just walk you through real quick the properties of the normal curve, or the properties of the normal distribution. All right. Is everybody okay if I go to the next slide? All right, so these are the properties of the normal density curve. Okay, so when something is normally distributed and you sketch its density curve, the density curves always have these properties. Okay. The first thing is it's symmetric. The curve is symmetric about its mean. So when you draw this distribution, you're going to notice that we're going to draw these number lines. We're going to draw these curves. And the curve is going to be symmetric about whatever I tell you the average is, the mean is for the random variable. So what this means is you could take this graph and you could literally like cut it down the middle. And when they're symmetric, it means you could fold the two sides onto each other and they would be mirror images of each other. That's what it means to be symmetric. When something's normally distributed, what happens is the mean is equal to the median is equal to the mode for that random variable. Those 3 measures of central tendency are the same. So this curve has a single peak, okay? And you can see it here has a single peak. And the highest point of the peak occurs when x is equal to the average, okay? It's like a sundae with a cherry on top, okay? There's the highest peak. Because this is a density curve, the total area under the curve is 1. So again, what we're going to do is we're going to relate area under the curve to probability. So what we're going to be doing is just like we did before, we're going to be shading an area on the curve and shading areas under the curve and finding the area under the curve. And because it's symmetric, the area under the curve to the right of the mean, so the area all the way here is equal to 0.50, and the area all the way to the I did it backwards, to the left and to the right is 0.50. Okay. All right, so let me try to explain this in a way that makes sense. Would you guys agree? Let me know in the chat. Do you guys think that heights of adult males follow a bell curve shape? Like, let's just say the average height of adult males is 5'10" in the United States. Okay, so that means the majority of males are somewhere, I don't know, a couple inches greater. 1 and 2 twice instead of 3 and 4. Where did I do that? In the notes, you wrote 1 and 2 twice. Where did I do that? I see 1, 2, 3, 4.
On the notes that we printed out, like where 3 and 4, it just says 1 and 2 also.
Oh, I don't know why that happened. Sorry about that. On mine, they look good, right?
Yeah, just like what it says is fine, but the numbers are just still 1 and 2 on
Okay.
the 3 and 4.
I am sorry. Yeah, mine doesn't. Mine matches you. Mine, you guys see what I see? Uh-oh.
I guess it's just me.
I guess it's just you. I guess you have a faulty PowerPoint or the PowerPoint, gods are playing tricks on you. I don't know.
Oh, well.
They're tricksters. Anyways, to go back, let's just say that heights of adult males follow a normal. It can happen if you use Keynote instead of PowerPoint. I don't know what Keynote is. Is Keynote like some Apple product? Oh yeah. Apple products are terrible outside of the iPhone. Sorry. I am a Windows computer person. Mostly because my wife is a Mac person, and every time her laptop dies, it's like another $2,000, and it's like, oh my gosh, you could just buy a Windows one for $150 or something. All right, but let's sorry about that. I digress. Anyways, what I was saying is like, let's say the average height of adult males is 5'10". Okay. What that means, if heights are normally distributed, is half of adult males are above 5'10", and half of adult males have heights below 5'10". That's all this means. Okay. With the area to the curve, area to the left and right is 1/2. Okay. These here, as x increases without bound, or on the flip side, if x decreases without bound, what happens is the graph gets more and more closer and closer to 0. So you'll notice, like when I sketch these graphs, I'll always leave a little space above the horizontal axis here. But what's really going on is when you get really far out, it's going to get really, really close to the horizontal axis. And then the one rule we're going to use today that's the most important is this thing called the empirical rule. And now I actually talked about this like during the second week of class. Does anybody remember me referencing the empirical rule when we were talking about the standard deviation? Does anybody remember? I'm just curious. It's okay if you have no one remembers. It's all good. But what it said is the following thing, okay? And it says approximately 68% of the total area under the normal curve is somewhere between, falls between x, if you take the mean and you subtract a standard deviation, and you take the mean and you add a standard deviation. So like, I'm just gonna go to the next slide and show you, okay? Here's a normal curve, okay? Here's the mean, whatever the mean is. If you take the mean and subtract a standard deviation, and you take a mean and you add a standard deviation, do you guys see this turquoise type teal? I guess it's more teal shaded area right here. Do you guys see this? what that means is 68% of the area under the curve falls from here to here. Okay, 68% is in this teal colored area. So that means instead of writing it as percentage, since the total area under the curve is 1, that means the area from here to here is 0.34, and the area from here to here is 0.34. So you can expand on this then. You can say 95% of the area is between, if you'd go another standard deviation, so mean minus 2 standard deviations to mean plus 2 standard deviations. So if you go from here to here, that's 95%. Okay. So what that also means, you'll notice I broke it up here, is you go from the mean out to here, half of 95 is 0.475. And half of 95 below is 0.475. So if you take 34 plus 13.5, you get 47.5. That's where this 13.5 comes from. Okay. So from here to here is 47%, but from the mean to 1 standard deviation is 34%, but from 1 standard deviation to 2 standard deviations, it's only 13.5%. Okay. And you can go on even further. 3 standard deviations on either side gets you to 99.7%. Okay, and then just note, we can have observations more than 3 standard deviations from the mean. It's just they're not very likely. Okay, they're just not very likely. All right, this graph right here, if you printed out the notes, okay, have this sheet of paper, like pull it off to the side when we go to do our first example, because this sheet of notes is going to be the most important problem that our most important piece of information we're going to use to answer questions. Okay, and just like the uniform problem, did you guys find, like, when we did the uniform problem, it didn't make sense till we did our first example? Did you guys feel that way, and then it kind of started making sense?
Yeah, it's initially very confusing.
Yeah, and this is going to be the same thing with this. Like, at first, this doesn't make any sense, and then once you see an example, I promise you, it'll make more sense. Okay. Is everybody ready if I go to the next slide? Okay. All right, so normal curves all have this overall bell-shaped curve, but you can have different things that are normally distributed. So here's 2 different normal curves, like one in pink, one in blue here. This is a mean of 0, standard deviation of 1. So it's centered at 0 and has a standard deviation of 1. This normal curve has a mean of 3 and a standard deviation of 1. So it's like the same curve, it's just shifted. So like the curves are just centered around the mean. Like this pink one, when the mean is 0, it's centered around 0. And this one, when its mean is 3, it's centered around 3. Now here's 2 curves, okay? A pink one and a blue one again. Now the pink one is centered at 0. And so isn't the blue one. Blue one is also centered at 0. You'll notice the pink one has a standard deviation of 1 and the blue one has a standard deviation of 2. Well, the smaller standard deviation means this curve is taller and skinnier. The higher standard deviation means the curve is shorter and fatter. That's really, or shorter and wider, another way to think about it. But they still ultimately have the bell-shaped, okay? And the most important thing is, just like this one and this one, the area under the curve is 1. And that's the most important thing. All right, we got 15 minutes of class left. So let me just try to do, let me just get through these first 3 questions here. Okay. All right. Everybody ready to just do one example and then we'll call it quits for today?
Can you go back for one moment?
Of course. Of course.
Thank you.
Yeah. All right. One example. So here's the problem. Suppose that talk time on the iPhone 10 is normally distributed. So what talk time is if your phone is fully charged and you call somebody, okay, and you have no other apps running, anything, you just call somebody, it's how long you could talk to them before your phone dies, okay? Now, do you think every iPhone 10 out there has the exact same talk time? Yeah, no, right? Like, people have used their phone differently over time, probably, how much pictures and apps you have on your phone influences it. So everybody's iPhone, I don't even know what iPhone I have. I think I have an iPhone 8 actually, or I might have a 10. I don't know. It's one of those things my wife just gets for me. So I don't, she just hands it to me and I'm like, oh, thank you. So I don't know. You guys are like, who cares? I just get on with the problem. But so all the talk times are different. So iPhone 10, the talk time is normally distributed. And what we're saying here is that it has a mean of 20 hours. Okay. So I'm giving you the mu, and it has a standard deviation of 5 hours. Okay. So notice I'm giving you in the problem mu and sigma. And let me just go back for a second. Do you see mu and sigma here? Mu and sigma here? Does everybody see those on this graph down here? So now I'm literally giving you these numbers to replace mu and sigma with. Okay, so here's what I'm going to do. Suppose an iPhone 10 is selected at random. Okay, and what I'm going to do is I'm going to record its talk time. Okay, so I'm going to define this variable. Okay, I'm going to let x, the random variable x, be the talk time on a random iPhone 10. I know I'm just rewriting this. Okay, so now here's the thing. When I grab somebody's iPhone 10, do I know for sure how long its talk time is going to be, or is it some unknown variable? Yeah, it's unknown. It's unknown. So this is this x is a random variable. Okay, it's a random variable. All right, is everybody okay if I go to the next slide real quick? Okay. So I just want to get these 3 questions in. So is x talk time, is it a discrete or continuous random variable? So does talk time have a finite number of outcomes? Is it a count, or is it a measurement of some type? What do we think?
Measurement.
I didn't hear you. I'm sorry.
A measurement.
Did you say continuous?
It's
a measurement. Yes. So, yeah, I got you. Yeah. So X, since it's a measurement of time. Okay. So the time you spend talking is a measurement. So Bertha, it wouldn't be discrete. It would actually be continuous. Okay, so here's what else we said that's really important. We said that X, the talk time, is normally distributed. So what I want to do here is I want to sketch the density curve, okay, for this random variable X. So we need to sketch the density curve for a normally distributed random variable X. Okay, so what does the density curve look like? It's just this right here. And what we have to do when we sketch the density curve is instead of writing mu minus 3 sigma, we actually put the numbers in, okay? So whenever you're going to sketch the density curve for something that's normally distributed, start by drawing a bell curve, okay? Hey, man, that looks pretty good, right? Would you guys say? Everyone's supposed to say yes, it looks great. Thank you. Thank you. I appreciate it. It's a little late, guys, so, but it's all good. I should have been an artist, I know. All right, so look, these curves are centered at the mean. Okay, so look where this dot is, all the way down to mu, the mean. What did I say the average talk time was? How many hours? Did I say it was 20 if you look back? Yep, thank you. Thanks, guys. And then next, what you have to do is you have to add a standard deviation 3 times. So if you look, I said a standard deviation was 5. So I'm going to go, here's 20. I'm going to add 5 to it. I'm going to get 25. I'm going to add another 5. I'm going to get 30. I'm going to add another 5. I'm going to get 35. And then I'm going to do the same thing on the other side, except instead of adding, I'm going to subtract. So 20 minus 5 gets me 15, 10, and 5. All right, so here's the one question we're going to end class on then. What? Oops, sorry. It's my wife texting me something. What is the probability? Okay, so I'm asking you for probability that the talk time for a randomly selected iPhone 10 is between 10 hours and 25 hours. Okay. So look, I want to find the probability that that talk time X is between 10 and 25. All right. Believe it or not, okay, I've actually given you enough information to be able to solve this problem, okay? So do you guys remember, did anybody remember what I said the most important concept of today is? Something about area under the curve is equal to probability. Right. So since we only have like 5 minutes left, I'm going to quickly just burn through this for you. And then I promise you we'll do another one next class. Well, look, I want to be between 10 and 25. Well, look, here's 10, here's 25. So what I'm going to do is I'm going to shade the area I'm interested in. I'm interested in this area over here and this area over here. And what I'm claiming is these 2 areas here, when you add them together, they're going to give me this answer right here. So let's find this area right here from 20 to 25. Well, look, that's from the mean to 1 standard deviation above. So from 20 to 25 is the mean to 1 standard deviation. Well, look, from the mean to 1 standard deviation, that area is 0.34. From here to here, 0.34. Now to go from 20 all the way down to 10, that's 2 standard deviations. Now watch. To go from here, 2 standard deviations. That's 0.34 plus 0.135 because it's both these two areas here. When you add this and this, you get 0.475. So this problem is just 0.475 plus 0.34, which is 0.1 or 815, I believe. And that's how you answer that problem using that little chart there. All right, let me ask you this because the chat got a little silent there. Does it seem like drinking from a fire hose? Like it's pretty confusing? Anybody still with me? Everybody, say that again.
It's not so bad. Initially, it looks like it's bad, but kind of better now.
Yeah, I promise you guys we're gonna do. We'll do some more examples on Tuesday. And I promise we'll make this a little bit easier. And the more examples we do, the better it'll be. So let me just go stop the recording.